Let us take some problems relating Kirchhoff's rule and effective resistance of some cells or some circuits. This is a question like the 12 resistors, each of resistance molar, are the sides of a cube as shown in the figure. Then what is the effective resistance about the main diagonal or about any side or about a diagonal on the base like that? In the present question, it is asked as what is the effective resistance about the main diagonal. Now we have to see that this is the point about which current enters and this is the point about which the current leaves. Now there are so many paths for the current to flow. It may be A, B, C, H, A, B, G, H, A, F, E, H, A, F, G, H, and so on. There are so many paths. So whichever the path, the current has to pass through 3 number of resistors. That's why here any current incoming or entering will be equally divided here. H for current entering A and leaving H, it has to come across 3 resistors. Whatever the path, that is ABCH, ABCH, ADCH, AFEH, etc. Therefore, current is equally divided. Current is equally divided at A. Let 6I the current entering so before applying Kirchhoff's rule, we have to find out the flow of current in the network. As seen, this 2I again divided II and ultimately united 2I. So the figure is complete. So potential difference across VAH, taking any path, suppose I consider ABCH, then you can say that 2IR plus IR plus 2IR, that is 5IR. Again, if R the effective resistance, then VAH is equal to 6I into R. Equating the two, you can write 6IR is equal to 5I small r or r is equal to 5 by 6 small r. If small r is given, then capital can be obtained. Now, if it is asked about a side like AB, then division of current will not be same. It will be different depending upon the path of selection. Suppose he asked H, what is the effect resistance about this current entering this way and leaving? So in this case we cannot take it as 6I because here any current moving from A to B has to come across one resistance. If there is another path A, D, C, B, so there are 3 resistances. If it is a path like, then there are also 3 resistances. So, what is the current across? Suppose this is I1, and for this there are 3, and for this also 3. So, this current will be same. So, when it is asked about a side or diagonal or like that, in that case we have to find out the division of current and number of resistors involved in each path. Again, this current here it will have 2 arms, and accordingly it will be time taking, and we have to find out how the division of current is there. Let us take another example like this is an infinite series R2R, R2R. Calculate the effective resistance of the infinite series so we have to see as what is repeated. This is the combination which is repeated in the series. Let R the resistance of the infinite series. So you can say that about AB, resistance is R. As it is an infinite series, by addition of one more repetition, practically there is no change in the series. Since an infinite series by addition of one more repetition, there is no change in effective resistance. Now let R dash the resistance across CD. Let R dash the resistance across CD. Here you can see capital R and 2R are parallel, with which it is in series. So effective resistance of 2R and R in parallel is 2R by 2R plus R. Now R dash is equal to small r plus 2R by 2R plus capital R. So this is the effective resistance about CD. But for the infinite resistance is R. Since it is an infinite series, by addition of one more repetition, there is practically no change to the resistance, that is R dash is equal to R, or capital R is equal to small r plus 2R by 2R plus R, or 2R plus R square is equal to 2R square plus 2R plus R square is equal to 2R square plus 2R. Two R square plus RR plus 2RR, or R square minus RR minus 2R square is equal to 0. So using quadratic equation, R is equal to minus B plus minus B square plus 4AC by 2A. So this is small r plus minus 3R by 2. So it is 4R by 2, that is 2R. Because the negative sign is not acceptable. Similarly, if there is infinite series of any sequence, we can take the attempt by adding one more repetition and assuming that there is no change in the resistance. By such, let us see another problem. Suppose R1, R2, R3, R4. Another resistance is, or it is non-resistance, suppose 10 ohm. It is connected to a source of 10 volt with suppose this is a circuit like A, B, C, D. So it may be asked as what is the potential drop or current across the arms. Now, this is the positive of a battery. So any current I will move from positive terminal. So here at this point, the current let here it is I1. So this is I minus I1. If this is I1, suppose this is I2, then here current will be I1 minus I2. It is I minus I1. So here current will be I minus I1 plus I1 minus I2. That is, it is I minus I1 plus I1 minus I2. So I minus I2. I minus I2. Here again it is I. Calculate the current across the arms So before applying Kirchhoff's two rules, Kirchhoff's two rules, the flow of current across the arms is to be ascertained. So taking the positive terminal of the battery, if there is one battery, we can assume the flow from positive terminal. And in this case, we can assume as current flow from C to D, or if we have also taken from D to C, no harm. Because if measurement of I1 minus I2 is positive, then our assumption is correct. Or if I1 minus I2 is negative, then your assumption is to be reversed. So even if I take this way, as per this way, as I like that, I could have summed up, or on calculation we can find out whether your assumption is correct or not. Again, before applying the second rule, before applying the second rule, we have to select as many loops but one as set of independent equations. Here there are three loops: A, C, D, A, C, D, B, C, and another, suppose A, E, B, D, A. Here there are three loops. A, C, D, A, C, D, B, C, and A E B D A. But all the three equations for the three loops are not independent equations, because addition of two equations is the equation for the third. If we take any two loops and have two sets of equations and add them, then that will be the equation for the third loop. So here we will take for the loop ADC, here current flow clockwise, here clockwise, here anti-clockwise. If there are only resistors, then potential drop in one way is positive, the other way is negative. So for this ADC we can write I1 R1 plus 10 into I1 minus I2 plus R3 into, sorry, it is minus because it is R3 into I minus I1 is equal to 0. This is one equation. And for CBD ADCA, this is CBDC. Similarly here, this is clockwise. If we take it positive, then the two are anti-clockwise, that will be taken negative. Or if we take these two as positive, that will be negative. So for this, it is I2R2 minus 10 into I1 minus I2 minus R4 into I minus I2 is equal to 0. If we add the two, let us see what happens. I1 R1 plus I2 R2, this will cancel. R4 R3. And there should be another equation for this one. That is also fourth loop. I1 R1 plus I2 R2 minus R3 I minus I1 minus R4 I minus I2. This is the loop. This is for the loop A, C, B, D, A. So there are four loops. This is 1, this is 2, this is 3, this is also fourth loop. So for the fourth loop, we can write this is a source supply. So you can say that where current flows away positive, then it is taken as negative. So again, we can take another loop A, D, B, E, A. For this, R3 into I minus I1 plus R4 into I minus I2 minus 10 volt is 0. So since there are four loops, so any three equation can be taken as independent equation. But out of these three, first three, we can take any two. This loop, this two loops, or one with the this, and this can be taken as the third loop. But from the first three, we cannot take the three as independent. So out of the three, we have to take only any two. If R1 by R2 is equal to R3 by R4, then the bridge is balanced. In that case, there is no current flow across CD. Then I minus or I1 minus I2 is 0. So any current entering will go that way, and this current will go the other way. In that case, so in the first case, as we have three equations, so we can solve if at least there are three unknown quantities. So out of R1, R2, R3, R4 and I1, I2, if any three are given, the remaining four unknown quantities can be evaluated. But if the bridge is balanced, then we can say that the equivalent circuit will be like this. If this is the condition, then we can say that the bridge balance. In that case, the current across R1, R2 is same. Suppose it is I1 and this is I minus I1. If I is the current from the source. So here we can get the effective resistance like this is series, so it is R1 plus R2 and this is R3 plus R4, and now the two are in parallel, therefore 1 by R is equal to 1 by R1 plus R2 plus 1 by R3 plus R4, and we can find out the resultant or effective resistance of the combination. Suppose a circuit is given like 6, 4, 6, 4, 8, 3, 5. Suppose the circuit is like this. It asked us what is the effective resistance about AB. Calculate the effective resistance across AB. So it is a Wheatstone's bridge principle where you can apply that principle. Let us see whether it is balanced or not. As observed, AC by BC is equal to AD by BD because it is 6 by 3 is equal to 8 by 4, that is 2. So it is a balanced bridge, so there is no flow of current across this. Therefore, the equivalent circuit is like this. So if there are there is a mesh like this, 5 resistors in the sense, let us see whether it is balanced, or if the product of 6 into 4 is 8 into 3 equal, then this is also balanced. So in that case, we take the situation like this, 9, 12, and effective resistance is 9 into 12 by 9 plus 12 is 21, 9 into 12, so 3, 7, 3, 36 by 7 ohm. Internal resistance of a cell using potentiometer principle. So we know potentiometer is a system where a wire of length AB or is connected to a source, emitter, rheostat, and a key. This is a long wire which is connected to a source through a rheostat, a variable resistance, key, and emitter. So the value of R is selected such that for full scale division, the potential across AB is more than the potential of the source for which internal resistance is to be measured. Let us take a jockey. The EMF, the internal resistance for which the internal resistance of the EMF of the cell is connected as shown in the figure. As shown in the figure. By adjustment of rheostat, the potential drop across AB is more than E. So it should be more than E. When key K2 is open, so when key K2 is open, then this measurement across the potentiometer wire is the EMF, because there is no flow of current in the circuit. So across the AB is, when key K2 is open, the potentiometer or the potential difference across AJ1 of length L1 is the EMF of the battery or EMF of the cell, that is E is equal to phi into L1, where AJ1 is L1, and this EMF is also I into R plus. Now when key K2 is closed, let AJ2 is L2, the point for which null deflection calorimeter is obtained. Then now when there is current flow in the cell, the difference is the potential difference V, or V is equal to phi L2, and this V is equal to IR. Now E by V is equal to L2 by L1. No. E by V is equal to L1 by L2, or I into R plus R by IR is equal to L1 by L2. Or R plus R by R is L1 by L2, or 1 plus R by R is L1 by L2, or small r is equal to R into N1 by L2 minus 1. Thus, internal resistance of the cell can be obtained if L1, L2 are measured from the potentiometer, where